Hello, and thanks for using TickBoom. In this video, I'm looking at question 6 of our 6-part question on volumes of revolution. So we've come to the last of the questions, and this one says, evaluating volumes by use of cylindrical shells is not always better than by use of circular discs. Consider the following situation. The region bounded by the curve y equals sine x, the y-axis, and the line y is equal to 1 in the first quadrant is rotated about the line y equals 1 to form a solid. So just like question 5, this question has 3 parts. Part A says use the method of slicing into disk, which is an extension 1 technique, to find the volume of this solid. Part B says use the method of cylindrical shells to find the volume of this solid. So in theory, those 2 different methods should give us the same answer. That's how we know we haven't made a mistake. And then part C says discuss why the method of slicing into discs might be more effective in some situations. Alright, so here we are doing question 6, and I'll start, so we'll start with part A, where we want to use slicing discs as the technique. So I'll just draw up the curve that we're dealing with. It's always a good place to start with these questions. So we'll have our x and y axis. Here's 0. Now here we're looking at the sine curve and rotating about the line y is equal to 1. So maybe I'll just define this as 1. And so I'll draw that curve y is equal to 1. And it's around this that we're going to rotate, which is slightly different to the other questions where we were rotating about the x or y axis. Although it doesn't really matter. Technique is very similar, you just need to be careful, a bit more careful with what your radius will be, as we'll see, but otherwise it's basically the same idea. So now let's just draw, maybe I'll call that pi on 2. I'll call that pi. And in terms of our sine curve, we know that it will hit 1 at pi on 2, and it will hit 0 at pi. And that's kind of all we're actually really only concerned with the positive quadrant, so we don't really care how the curve continues down here. And also we're only concerned with the part that's bounded by this sine curve and the y-axis, and this line y is equal to 1. So we don't actually care about this bit either, only this bit. And basically the method we're going to use for part A is we pick a slice, and then we rotate that slice around the axis, and we repeat it for all the values in the region that we care about. So here between x is 0 and x is equal to pi on 2. So here the area of this slice, when we rotate it, it'll be kind of like a coin, as we've seen in the prior questions. The area of that coin will be pi times the radius squared. And in this case, the radius, it's not y or x like we might have seen in other questions, but it's actually the distance from here to here, which is 1 minus y. So that's where you need to be really careful. But once we've noted that, basically we can say the volume that we're going to get will be the integral between our x values of 0 and pi on 2. And the volume of the slices as we rotate will be pi times 1 minus y squared, because it's the radius squared, and then dx is the width. So basically we just want to put y in there. Well, y is equal to sine x, that's the curve. So this will become, maybe I'll just bring the pi out because that's a constant. Integral from 0 to pi on 2 of 1 minus sine x squared dx. And here I might just expand this, so we'll get pi times the integral from 0 to pi on 2 of the first one squared minus twice the product plus the last one squared. And now I can kind of integrate each of these bits, and the only thing worth noting in terms of integrating sine squared x is we can note that sine squared x, one of our identities would lead us to this being half minus a half cos x, and cos 2x. Sorry, using the identity for cos 2x, we can get sine squared x is a half minus a half cos 2x, and that's going to be a bit easier to integrate. So, alright, let's do it. So we'll have our pi out the front. The integral of 1 dx will just be x. The integral of 2 sine x, or sorry, the integral of minus 2 sine x, that would become plus 2 cos x. And now integrating sine squared x, we'll just integrate a half minus a half cos 2x. So the half will just become x on 2. And then the minus a half cos 2x would become, would be minus a half. And then we're effectively doing a u substitution here, which would get us to sine 2x times a half again. And if that doesn't jump out at you, just feel free to work through the u substitution for cos 2x, and you'll see that you get this extra half out there when you're working out du dx or dx du. When you're basically working out dx, you'll get du on 2. And that's all between 0 and pi on 2. And so now we just need to evaluate these. So we'll have our pi out the front, and so we'll get pi on 2 plus 2 cos pi on 2. And this will become pi on 4 minus a half times a half will be minus a quarter. Sine 2 times pi on 2 will just become pi. And then from that we're going to minus 0 plus 2 cos 0 plus 0 on 2 minus a quarter sine 0. And what does that give us? That'll give us, I'll just get my calculator. So what's cos pi on 2? Well, cos of 90. That's just going to disappear. That'll be 0. Sine of 180 will also disappear. And sine of 0 should also disappear. And then cos of 0 should be 1. So, so what do we get here? We'll have, so this will go, and this will go. So we'll have pi on 2 plus pi on 4 minus 2. So that'll be a half plus a quarter will be 3/4. It'll be 3 pi on 4 minus 2. Or if I multiply the pi through, it'll be 3 pi squared on 4 minus 2 pi. That's how that will all expand. And then we just got to remember our units. Units cubed.
Panic boom!
Alright, so that's what we get for part A using this method. So I guess what we'll do now is we'll work through part B, and hopefully, even though we're using a different method, we get to this same result. If we don't, then we must have made a mistake somewhere. So I'll just turn over to do part B. I might I might draw the diagram up again just so that I can then annotate on the cylindrical shell approach. So just bear with me as I redraw this. X, Y, 0. We'll do, we'll call that 1. So we'll do, this will be y is equal to 1, and we're still rotating about that line. Call this pi on 2. Call that pi, and so on. So the curve will look like this. We don't really care about anything else. This is the main bit that we're concerned with. And with the cylindrical shell, what we'll do is we'll draw a horizontal line this time with its thickness. And we then rotate that around the line to create a cylinder, that kind of old paper mache idea. And then it's about understanding that if we take that cylinder, slice it and unwrap it, what would we get? Well, we'd get a rectangular prism. And I should have mentioned at the beginning, if you haven't watched videos 1 to 5, I definitely recommend watching those, because a lot of what I'm covering here I've explained in detail in those videos, which is why I'm kind of just working through it without really explaining it. The assumption is you've seen the detailed explanation in those prior videos. So here, this width here would be dy. It's a change in y for our width. Our height of this cylinder is just our x value. And then the length of the cylinder is essentially the circumference. And the circumference of a circle is 2 pi r. So we'll get 2 pi. And in this case, the radius, just like it was in part A, it's 1 minus y. 1 minus y is the radius. So they're the kind of ingredients. So for this technique, the volume will be equal to the integral. And this time, because we're doing dy, we want to look at our y values. So we're going to be looking at between 0 and 1, because they're the y values that we're concerned with. So between 0 and 1 of our 2 pi 1 minus y times x times dy. And so it's about evaluating that. Here, in terms of, it will probably be easier to integrate this with respect to x. So we can insert y is equal to sine x, just like we did with part A. But this dy we're going to need to get into dx. So just over to the side, we'll note if y is sine x, then dy dx would be equal to cos x. So that means dy we could write as cos x dx. So that means I could bring out the 2 pi, the constant, and that's going to be the integral from 0 to 1 of bracket 1 minus sine x times x. And now, instead of writing dy, we can write times cos x dx. And now let's clean this up a little. It's probably going to be helpful to expand all this. So we'll get 2 pi times the integral from 0 to 1 of x cos x minus, and we could write this as x cos x times sine x dx. And what we'll need to do is look at each of, well, we're going to need integration by parts, and it might be helpful to just do each bit separately. and then bring it all together. So if I focus on this bit first, if I'll just put it off to the side here. If I think about the integral from 0 to 1 of x cos x dx, well, my integration by parts, I want to think of it as the integral of uv dash is equal to uv minus the integral of vu dash. That's the basic idea. So I want to pick which one should be u and which one should be v dash. The cos x, or if it was sin x, they're always the better candidate for the v dash because they flick back and forth as you continue to differentiate. So I think we should have in this paradigm u is equal to x, v dash will let be cos x. That means u dash will be equal to 1, the derivative of x is just 1, and that means v must be sine x because the derivative of sine x is cos x. So now we can do our integration because this integral will then become, if I evaluate, we'll have u times v, so x times sine x, minus the integral from 0 to 1 of v times u dash. So v is sine x times 1, so just sine x dx, and this is all between 0 and 1, and we see how integral of sine x dx is easy enough. So this then becomes x sine x minus, and then the integral of sine x would be negative cos x, so this would become a plus cos x, and this is all between 0 and 1, and I'll just have to turn over to continue this. So what we'll get, and actually I wonder, I think something I missed, but I've just noticed, is that when I switched from going with respect to y with respect to x, actually that means we flip from going from 0 to 1 to 0 to pi on 2. So actually from here I should really write pi on 2 wherever there's a 1. So this will be between pi on 2, pi on 2. I think what I just did there is a really common mistake where you forget as you switch from one variable to the other, you need to remember to switch your boundaries of your integral. So good thing I picked that up. I mean, at the end of the day, I would have ended up with something very different to this, so that would have triggered me to go and check. But now I'll turn over to continue that. So we're going to say the integral from 0 to pi on 2 of x cos x dx. That's going to be equal to, and we'll have pi on 2 times sine pi on 2 plus cos pi on 2 minus 0 plus cos 0. So we'll have 0 plus cos 0. So sine pi on 2, or sine 90, this bit's just going to be 1. Cos 90 will be 0, so that will disappear. And then cos 0 is 1. So we'll get pi on 2 times 1, or just pi on 2 minus 1. Now that bit is just the first part of this integral. So now we're going to do the next part of the integral. So we're going to look at the integral from 0 to pi on 2 of x cos x sin x dx. So let's have a look at that. The integral from 0 to pi on 2 of x cos x sin x dx. And I'll just note off to the side, what's going to help us here is that we know sine 2x is equal to 2 sine x cos x. So what that means is this kind of cos x sine x is a half sine 2x. So I can say cos x sine x is just a half sine 2x, and that's going to be easier for us to integrate. So this integral then becomes the integral from 0 to pi on 2 of a half x sine 2x dx. And then this integral becomes quite similar to the one we just did. We'll just use integration by parts again. So I'll just bring out the half. So that's going to be a half times I guess I can write, I'll just write up my integration by parts formula, and we'll decide what we want x and or u and v dash to be. So we'll have the integral of uv dash is equal to uv minus the integral of vu dash. So here, and I'll just get my brackets ready. So here we'll want, I think as before, we're just going to want u to be x and v dash to be sine 2x. So that means u dash will be equal to 1 and v will be, this would become negative a half of cos 2x. And that's, again, effectively using a u substitution, just kind of doing it quickly in my head. But again, if that's not something you're super comfortable with doing, just feel free to do it out in full, and hopefully you'll see this is what you'll get. And if you were to differentiate this, you'll get back to sine 2x anyway as another way to check. So, okay, so what does that mean? That means the integral is going to be u times v, or x times negative a half. So it'll be x times negative a half cos 2x minus the integral from 0 to pi on 2 over v, which is minus a half cos 2x, times u dash, which is just 1 dx. So that's between 0 and pi on 2. So this will be a half, and this will just be negative x cos 2x on 2. Then this becomes plus a half. Then the integral of cos 2x will become a half sine 2x. And then that's all between 0 and pi on 2. So now we can start to evaluate this. So we'll get a half times, and we'll put our pi on 2 in first. So we'll get negative, this will become pi on 4. So negative pi on 4 times cos of 2 times pi on 2, or cos of pi, plus this will become a quarter, and sine of pi. And it's going to be minus, and this will just become 0, or minus 0 is just 0, plus a quarter times sine of 0. So let's see what we get, and hopefully it is, we do end up where we got with part A. So the cos of 180 is, that's going to be negative 1. Sine of 180 we'll see is 0, and then sine of 0 is also 0. So this is going to drop away, this will drop away. So we're actually just going to end up with the negative 1 and the negative pi just becomes pi on 4 times a half, which is pi on 8. Okay, So now if we remember that we've just done each of these parts, so now the volume that we're trying to get to is going to be 2 pi times integral of x cos x, which we worked out was pi on 2 minus 1, minus the integral of x cos x sine x, which we just worked out was pi on 8. Okay, so the pi on 2 minus the pi on 8 would become, that's 4 pi on 8, 4 minus 1 is 3. So we're going to get 2 pi times 3 pi on 8 minus 1. And then effectively the 2 and the 8 will simplify to just be pi on 4 pi. So it's going to be 3 pi squared on 4 minus 2 pi units cubed. 3 pi squared on 4 minus 2 pi. And what did we get for part A? 3 pi squared on 4 minus 2 pi. Okay, so using both of these techniques in part A and part B, we do get the same answer, which is good. Now part C, and I'll just kind of write this off to the side here. Part C said, you know, use this to kind of explain why sometimes using slices might be better than using cylindrical shells. Well, in this case, I'll just write it as slices resulted in an easier integral. That's pretty much, I think, what the question writer is trying to get us to realize. When we use cylindrical shells for this particular problem, we ended up with quite a messy integral. You know, we had to use integration by parts twice, and that's just a much more involved set of techniques than what we had to do in part A, which was really just basic integration. So I think what this question's really trying to get us to appreciate is that we've got these two techniques, the kind of slices and cylindrical shells. They'll both get us the same answer for the same volume of revolution. So we really have a choice. We get to pick, and I guess as you practice this more and more, you'll start to develop a bit of an intuition as to which one's going to result in the easier integral. And even if you haven't got that intuition, you can try one of the techniques, and if the integral turns out to be a bit of a nightmare, you always know you've got this other option up your sleeve that you can try and see if maybe that gets you a better integral. So there you have it. That's the end of that 6-part series of questions. I think a really well written set of questions. I think they do a good job of guiding you through these two techniques and kind of fleshing out kind of how they work and getting us to think deeply about those techniques. If you found this video helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.